We're happy to have Alex de Faveri who tell us about non-escape mass for quantum limits on hyperbolic 4-manifolds.
Thank you. Thanks for the introduction and for the invitation. Pleasure to speak in the seminar. So as the title says, my talk will be related to the quantum unique ergodicity conjecture. All of what I'm going to talk about today is joint work with Zvi, who is a member here at the IS. I think Zvi gave a short talk about QE recently, so I'll give just a little bit of motivation, but I'll be relatively brief. The setting is a compact manifold of negative curvature, which we'll call X, and we take a nice orthonormal basis of L2 of X, consisting of eigenfunctions of the Laplacian over the manifold with eigenvalues lambda I. They have nice physical significance. So, for instance, they quantize the Billiard dynamics in X, which is chaotic due to the curvature assumption. And one of the guiding principles that I want to keep in mind for this talk is this principle that the phi I are expected to behave like random waves as the eigenvalue goes to infinity. So this is sort of more of a vague philosophy, and this can be made formalized in various different ways. So there is a lot of work on LP norms of such eigenfunctions. But for the purposes of this talk, we're thinking about a weak version of this phenomenon in terms of distribution of L2 mass. And then the quantum unique ergodicity conjecture of Rudnick and Sarnak says that if we take these probability measures mu I given by the L2 norm, notice that I'm normalizing so that the phi I have L2 norm 1, so these are genuine probability measures. They should converge in the weak star topology to sort of the canonical thing you would expect, just the volume measure. So that's the conjecture in question. So this is generally open for any manifold, but there's been a lot of progress in arithmetic settings of this conjecture. So what I'll be calling an arithmetic manifold, maybe I should say a congruence manifold more precisely. G here will be a nice Lie group, K is its maximal compact, and we'll take a quotient by a congruence lattice. So a lattice given by some nice congruence conditions. That's the arithmetic structure. And the sort of guiding example is the case of SL2Z, where we get the usual modular surface, the upper half plane modulo SL2Z. And notice that I sneakily dropped the compactness assumption, but there are adaptations of the quantum unique ergodicity conjecture to this setting. So here, the arithmetic really comes into help because you have extra averaging operators, the Hecke operators, which commute to the Laplacian. So instead of taking any basis of eigenfunction of the Laplacian, we can take a very distinguished basis of eigenfunctions, which are also simultaneous eigenfunctions of the Hecke operators. And that's what we'll do. So we restrict the problem, make it a little bit more tractable with this extra arithmetic assumption that the phi r are also eigenfunctions of the TP for every prime P. And that's what I'm calling the arithmetic quantum unique ergodicity. And in the setting of SL2Z, or in the setting more generally of arithmetic surfaces, this is now a theorem, so comes from the celebrated theorem of Lindenstrauss, who settled the conjecture for compact arithmetic quotients. And in general, so in the setting of SL2Z that I'm treating here, showed that the only possible weak star limit points of this sequence of measures mu I are proportional to the volume. So of the form C times the volume form. So what remains in the case of SL2Z is to show that C is one, or in the case of non-compact quotients, it is a priori possible that C is not equal to 1, that this is what is referred to as escape of mass in this context. And this was ruled out in this case by Sound in 2010. So this completed the proof of AQE. So this is now a theorem for any congruent surface. So the case of 2 dimensions is well understood, at least with this extra arithmetic assumption. By the way, I should say, feel free to ask questions at any point and interrupt me. All right, but this talk had 4 manifolds in the title, so I should tell you about HM, which is the upper half space, the n-dimensional upper half space. And one of the ways of modeling the isometry group, so this is very, very classical, at least from the 50s, is it's possible to model it as a group of 2 by 2 matrices. Of course, you can model it as SO1n, but it's also possible to model it as a certain group of 2 by 2 matrices, which is in the literature referred to as SVn-2 for normalization reasons. So we're going to consider the arithmetic quantum unique ergodicity conjecture for these manifolds Xn, which are sort of the simplest arithmetic quotient of upper half space, given by the integer points of this group of isometries. And just some examples here. So in the 2-dimensional case, you indeed have the usual modular surface. In the 3-dimensional case, you have a quotient of SL2C by SL2 of the Gaussian integers. So, by the way, in this 3-dimensional case, this conjecture is also solved. So in this case, things were a little bit backwards. So non-escape of mass was proved quite early on in the master thesis of Asif Zaman. And the methods of Sound more or less apply, just changing primes to prime ideals, because you're in the setting of SL2 over number field. And then the equidistribution result is by Shem-Tov and Silberman, which is more recent. All right, so if you really want to see what this group is, it's this nice algebraic group here. It's a sort of symplectic group, but that's the quotient that we're treating. And some observations about this quotient is that there is no direct connection between QE in this context and the L functions, in part because, at least as far as I know, there is no proper analog of the Watson-Ticino formula. So for instance, QE, as far as I'm aware, doesn't follow from the generalized Riemann conjecture. Also, this space has some interesting violations of a naive version of the Ramanujan conjecture due to certain lifts from half-integral waveforms. All right, any questions so far? Okay, so what we show is that in the context of these 4-dimensional manifolds, escape of mass cannot happen. So any weak star limit point of these measures mu I has to be a legitimate probability measure. Sorry. And I should say that more is known, so there are results towards equidistribution by Zvi and Lior, which say they precisely locate the remaining difficulties. So it says that the possible limiting measures have to be linear combinations of the expected volume measure and possibly volume measures on these codimension 1 submanifolds. So those are the ones that need to be ruled out.
So in the case you start off with other arithmetic groups which are quotients of SO4, 1, which are say compact quotient and which don't have these totally geodesic surfaces. I'm sure that they're easy to make. Then do we know QUE?
If you can make this.
Yeah, but so
Right.
you can't really make these constructions. It's a fact that
I'm not
every
sure.
every
Sure, tips that you don't have
constructions
constructions which don't.
will come from a quadratic form.
No, they don't only come from quadratic. They don't only come from quadratic. I'll show you.
In 5 dimensions, I believe.
5, I said 4. But certainly in 3, you can have the different types. We do know which have totally geodesic submanifolds. I mean, basically, they can. Their classification. Alan Reed's book, I think. Anyway, where's Milicevic? He's the expert at that. He studied the L infinity norms exactly when you have these totally geodesic. But the minute they're totally geodesic, you have problems, and if they weren't, you wouldn't have a problem. Is that correct?
Basically,
And also only the codimension 1 are a problem. Codimension 2 are not a problem.
Okay, so now I think ones that come from certain division algebras might be good for you. We can discuss them.
okay.
Okay, so any other questions so far? So the plan, I want to give you some ideas of the proof and the differences from previous work. But to do that, I sort of have to show you, at least give you an idea of the proof for SL2 Z. So that's what I'm gonna do very briefly. So the proof, so the basic idea is to use the Hecke operators to shift mass. So let's say you have some neighborhood of the cusp here, and you want to show that not so much mass for your eigenform is present there. Well, you can apply a Hecke operator, and the Hecke correspondence is going to give you these points and a point up there, but let's forget about that. So either by general just equidistribution of Hecke correspondences or by this very concrete picture, you might try to use the Hecke operators to shift this mass downwards. One way, of course, we're talking about L2 mass. So one way to do such a thing, you probably want to use some inequalities. You really need positivity. So of course, in this case, you can just use Parseval over the unipotent to pick up the Fourier coefficients squared. So in a sense, the Hecke operators are shifting the Fourier coefficients and shifting the height of the form. So you have to deal with this shifting of Fourier coefficients in order to be able to lower the height. So just to establish some notation, here's the Fourier expansion of our form, and K is as the Bessel function is completely irrelevant. So it's completely irrelevant for this argument. In fact, we don't even need separation of variables between N and Y. But this is what we have, and here are the classical Hecke relations. So it will be important to separate, have a distinction between Hecke eigenvalues and Fourier coefficients, because of course, in higher dimension, those are no longer the same. So let's keep this straight. But the basic Hecke relation, of course, and the workhorse for the argument of sound is this. And in particular, the Hecke relation implies this much used fact in all of analytic number theory that one of these two Hecke eigenvalues has to have some size, so they cannot be tiny because of this relation, right? And what sound actually proves is what I like to call a comparison inequality between Fourier coefficients. So if you take this little L2 norm over the Fourier coefficients and truncate at x over y, you get some gain when compared to the full sum up to x. So you gain something that goes to 0 with y. And very, very importantly, you get this completely uniform inequality. Uniformity is the name of the game here because, of course, you're going to want to take eigenvalues to infinity.
This is with the absolute value squared.
Yeah. So something with absolute values should also be possible here. But for this particular problem, this will come up. So absolute value squared. And in fact, this will be a big source of complications for us because we're going to want to use the Hecke relations, and they're very nice here. So you don't really, there's essentially no distinction between absolute value squared of coefficients and absolute value squared of this thing. You can just apply Cauchy with a constant number of terms. But in our case, the Hecke relation has an unbounded number of terms, and this will be a big source of complication. But let's not get ahead of ourselves. So the important thing is that we need something completely uniform. So many usual tools are out of the game, at least without some strong assumptions like Ramanujan conjecture, etc. But this particular game is irrelevant. In this case, it can be seen to be essentially optimal for sequences that satisfy the Hecke relation. Up to this log can possibly be removed, but you can't actually gain more than square root.
What about this coefficient? 10 to the power 8.
Sorry. So that's just what comes out of the argument, but it's just to stress that you need something completely uniform. So yeah, just, of course, any absolute constant there would be fine. All right, so first of all, why is this sort of inequality at all related with escape of mass? It's very easy to see that it implies non-escape of mass. So you just consider the L2 mass over this cuspidal region, this rectangular cuspidal region starting at height t. Well, that's the L2 mass. You plug in the Fourier expansion, you change variables and apply Parseval, and you got the sum of Fourier coefficients squared. And now you completely isolated the Bessel function. It doesn't matter what it is, but you have positivity. So you just apply this comparison inequality for this partial sum truncated at y over t. Well, you can compare it to the full sum up to y and gain this factor of root t, or this factor that goes to 0 uniformly in t, and that's the proof. Okay, so once you have this inequality, it follows directly. Of course, in many other contexts, this is not the case, but it is the case for SL2, and it will be the case actually for hyperbolic n space in general. Essentially because we have a billion nilipotents. All right, so how does the proof of this comparison inequality in the case of SL2Z? Let me first tell you what we do. So we do a similar thing. We prove a similar comparison inequality. So this is the Fourier expansion of a form in our arithmetic quotient in hyperbolic 4 space. This is very classical due to Maass in 49. Similarly looking, and we prove a similarly looking comparison inequality with, we don't write the 10 to the 8 because it would be quite ridiculous. And in fact, this R here is actually doing some work. It's not just coming from the primes, but yeah, if I have some time, I can talk about it. Yeah, I have no idea if this is optimal, but we gain something that goes to 0 uniformly with y. All right, so let me tell you about the proof for SL2Z first. So the name of the game are these sums of Fourier coefficients. Let's denote them S of Z. And here's the Hecke relation for your reference. So we want to show roughly that this thing compares favorably. We gain a root y. First of all, there's this standard fact in, say, the amplification method, this TP squared phenomenon. So for each prime p, at least one of these two Hecke eigenvalues has to have some size. So we're going to try to use them to amplify. So instead of using only one TP to shift mass, we're going to use many primes. So that's standard. So we choose a large set of primes, say around root y for technical reasons, because we may have to use p squared. Let's say they localize around some value. Okay, this is easy to arrange because if the primes are too large, you win very easily. So for the simplest case, let's assume that they all localize around L and it's lambda p. So what's Sound's idea? Sound's idea for dealing with these sums is to split it up into two pieces. The piece with many prime factors in our good range, so many prime factors in our set of good primes, and the ones with very few, with less than k prime factors in this set of good primes, where k is a parameter completely at our disposal. And then these truncated sums restricted to the corresponding number of prime factors can be dealt with separately. So let's talk about the case.
Slowly, you pass.
Oh, sorry, yes.
Takes time to read.
Yes, so we this is just some notation. So this will be the truncated sum restricted to less than k good prime factors. And this will be the truncated sum restricted to at least k prime factors.
Mm-hmm.
And it's not clear why this will come up yet, but let's try to deal with the sum restricted to the Fourier coefficients with not so many prime factors. In this case, we can do a sort of standard amplification. So we have these not too small Hecke eigenvalues at our disposal. So we can try to amplify. So we take this amplified expression. So this part is just this sum. And then we can multiply by a bunch of Hecke eigenvalues. So we have the sum over the Fourier coefficients with less than k good prime factors. And we amplify with all of the Hecke operators at our disposal. So this compares favorably to the full sum, right? Because this is guaranteed to have some size. So this term here, we have a bunch of primes. Maybe we have to remove some that divide n because for convenience, but there are few of them for these n, so at most k. And each of them we're assuming has some size L. So we get that we gain at least a factor of L times, say, root y. I'm ignoring logs for all of this. So this is a large multiple of the initial sum that we want to bound. And now the task is, how do we upper bound this whole expression in terms of a longer sum? So of course, we're going to multiply. So we use the Hecke relation for these multiples for an times lambda p. And in fact, for this case, we can arrange that they're coprime. So they literally multiply. We get just a sum of a and p's, but they could have high multiplicity, right? There could be many pairs NP that give rise to the same a and p squared. And this is precisely where this multiplicity assumption comes in, because if n has less than k good prime factors, then np has less than k plus 1 good prime factors. So it couldn't arise in many different ways from a pair n and p for n in this good set. So in at most k plus 1 ways, therefore we conclude that this amplified expression is just a bunch of Fourier coefficients which can have size, well, at most x over y, which is the size of n times p. And well, we chose p to be of size root y, so we get this, and the multiplicity is bounded by k.
In the sum, what happens with those numbers which don't have any prime factor in this, which is roughly square root of y? I mean, that sort of you need to also.
Yeah, so they
for many of them or something.
Yeah, so you're saying they don't even appear here.
Let's say in this upper bound. I mean, what do you know about the cases where?
In which upper bound?
In this lower bound to e.
Right here.
Yeah.
For the n which don't have any prime factors. Well, you don't have to subtract anything here, right? But you don't, k will be relatively small compared to root y, so you don't gain much. Yeah, so yeah, I just simplified this whole factor to root y. K will be, yeah, so this is definitely a concern, but in the end we choose k relatively small compared to root y. All right, so putting all of this together, we get that, well, this sum is at most a factor of k over L root y times a longer sum, still with a small number of good prime factors. And then you can iterate. In Sound's paper, it's not written in this way, but it's more convenient for presentation. You can iterate the same argument and get, well, you get another factor of root y here, you get another factor of k over L root y. And here I just completed to the full sum. You could have a less than k plus 2, but doesn't matter. All right, so the point is that for the sum over the Fourier coefficients with few good prime factors.
This technique is due to invariance.
Yeah, exactly.
Showing that without assuming Ramanujan, you have some a n squared is less than lambda into the x to the epsilon times x times lambda to the epsilon.
Yes, for Rankin-Selberg.
Just the sum of the squares.
Yeah,
relieves you of Ramanujan.
Right, exactly. And it's also used in the amplification method.
Of course, the other part is used in the amplification.
Right. Yeah. So this TP squared phenomenon also used in amplification. Yeah. So for this part of the sum, we're fine as long as k is not too large. So we will remember we want to win a 1 over root y, and it will be important to win that because we're actually going to apply induction. So as long as k is not too large, as long as k is at most L, which is the size of our eigenvalues, times y to the quarter, will be fine. And here you may complain because I told you k will be small. What if L is super large? But L will not be super large. If you have one incredibly large eigenvalue, you can use just that Hecke operator and you're fine. All right, so what about the other part of the sum, what I'm calling the highly divisible terms? So what are the Fourier coefficients left? The ones with at least k prime factors in the good set. So they're of the form an, where n is a multiple of some product of at least k prime factors in the set. Remember, this good set is the set of primes roughly of size root y. So very coarsely, the number of options for D is something like root y choose k, and D is of size root y to the k because the primes are of size root y. So lying a lot, for each choice of D, we have to face these highly divisible prime factors, right? Our sum goes up to x over y, so dm goes up to x over y. And here I like a bit, but using the Hecke relation in the opposite direction, you can identify a dm in terms of ad times am. Of course, there's another, there may be other factors, but roughly this is multiplicative. So roughly this is the same as lambda d times am, in which case, okay, we get a lambda d squared times the sum just with m's here, which is precisely the truncated sum. Okay, so lying a bit, there's, of course, sound does work here, but this essentially holds. All right, and the size of D is root y to the k, so this is roughly, and the size of each of the lambda p's is L, and this guy's is multiplicative, so this is going to be size roughly L to the k. So we get some recursive inequality for this this highly divisible sum in terms of shorter sums. Instead of the sum at x over y, the sum is at x over a big power of y. And here, it's not how it's written in the paper, but you can apply induction to this shorter sum. So we assume that we do have a gain of square root of the difference for these sums. So in the end, for the full sum, we have this number of possible d's. Then we have this sum for each of the d's. And if you work this out, so you have root y over k to the k from the binomial coefficient. You have an L over to the k here. And from the induction hypothesis, we get a root y and a root y to the k, so this y to the operator. And very nicely, what do we need to succeed here? So we wanted precisely s of x over root y as a bound, and this succeeds precisely if k is a bit larger than L times y to the operator, which was precisely the previous restriction. Of course, there's a game with constants and logs that has to be played, but it works. All right, so that's roughly how Sound's argument goes. Again, this idea of using many Hecke operators to lower the height, and dealing with the multiplicities issues that arise separately. Any questions so far? Okay, good. All right, so yeah, and of course, maybe the lambda p square, maybe the lambda p's are all tiny, you may have to use the lambda p squares. This works similarly. All right, so let me tell you about what happens for us and what sorts of obstructions that arise in our case. So the Hecke theory, we have something similar. In this case, we have two algebraically independent Hecke operators T1 and T2, and one can arrange for a sort of Hecke relation that by picking a nice third operator T3, so that at least one of the three eigenvalues is not tiny. So you can find some Hecke operators that such that at least one of them is guaranteed to not be tiny. So that's great. Again, the strategy will be the same. Let's try to amplify with these Hecke operators that have large Hecke eigenvalues or have not tiny.
At this point, when you're talking about Hecke operators, you're not talking about the cusp. You're just talking about the spherical Hecke operator, the spherical algebra, which is got two.
Yeah.
And these relations. In other words, it's in terms of the spectrum.
Yeah, this is just Hecke.
Nothing to do with coefficients.
Nothing to do with coefficients yet. Yeah, this is just Hecke. So if you want, you can do a computation of polynomials and get the exact relation here.
I'm just explaining why there are two of them.
Yeah, exactly, yeah. Yeah, and so
rank 2, it's because it's a rank 2 group over QP.
Yeah. At least for P greater than 2. Yeah. All right, so a similar strategy will be necessary here. So we need to treat these Fourier coefficients differently depending on their potential for multiplicity. So again, we're going to take this sum of Fourier coefficients, and we want to prove a comparison inequality just as before. So
P divides beta here is divisible.
Yeah, so all three coefficients are divisible by P. So there is potentially some room for changing this, but actually there are some serious difficulties with doing something else. Soon we're going to have quaternions, so one could get more stratified sets depending on quaternion primes, but yeah, this turns out to not be good. Yeah, but for now, it's just Z3, and I mean, P divides all the coordinates. All right, so once again, we're going to have to break the sum and treat differently the highly divisible terms and the terms with low potential for multiplicity. So for the terms of low potential for multiplicity, once again, we try to amplify. So let's take sort of this.
Just a minute. I'm unhappy about it's Alphonse who brought these funny 2x2 matrices into hyperbolic n space. You know that?
Yeah.
You love 2x2, but
that's what we follow.
And somehow, yeah, I'm sure you're following. I'm trying to understand, is that really necessary in your work? Because very few people use this realization. So why is it so important to think of this as 2x2 quaternion matrices? That was a bit of a shock to me.
So it's not clear. It's probably not important. So it's just very convenient because we do need somewhat explicit Hecke relations, and the Hecke theory was only worked out in this language, at least as far as I'm aware, by Pitale.
By who?
By Pitale.
You write it down.
Amia Pitale, yeah.
if you just use Whittaker relation between Whittaker models and Hecke operators, you don't see how to do it.
You mean for the actual Fourier coefficients?
You have a cusp, so you have Whittaker functions in the usual way.
Yeah, so this potentially could be done. Yeah.
Just try it. It's because it's an interesting.
Yeah, and another interesting.
This has nothing. The minute you put beta there, that's the cusp, right? That's Fourier coefficient.
Yeah, on the cusp.
So you haven't explained us the relation. All right, maybe it'll become clear.
Yeah, exactly. So I will display the Hecke relation shortly. So for now we have Hecke eigenvalues and we have Fourier coefficients and they have no relation. So let's try to implement the strategy in this sort of baby case where the lambda one, the eigenvalue for T1, which I didn't tell you what it is yet, has some size. And let's say it's of size 1, just to simplify our life. Let's say for all the primes in the range that we want, which turns out to be y to the 1/8 for technical reasons. So here's the Hecke relation roughly for T1. So here's what it does to Fourier coefficients. It's very similar.
T is a scalar and beta is a vector.
Yes.
Okay.
Yes.
Let's be clear.
Yes. So we changed.
For a guy who's talking very primitive stuff. Yeah, I want to know what's a vector and what's a scalar.
Yeah, exactly. So in fact, we change parameterization here. Now the arithmetic.
So this is a standard fact in higher rank. That the Hecke operators, the spectral theory of the Hecke operators, the Langland's Ramanujan conjecture is only about the spectrum. The Fourier coefficients are got to do with some expansion and are usually vectors. But the Hecke operators only operate as scalars. So if you go to SP2G, for example, then the Fourier coefficients have much more information than the Hecke eigenvalues. But they do give information in rays, and that's what you're going to be using. You multiply by a scalar P or another scalar, but the betas are vectors. Yeah, I understand now. So I'm sure you can do it the other way also.
Yeah. Okay, so this is the Hecke relation. It looks very similar to the SL2 relation, except we have this extraneous term here. So first of all, I changed parameterization. Now it's convenient to denote B as a traceless quaternion instead of an integer vector, in which case this Hecke action can be written nicely as just some conjugation, some quaternion conjugation, where here alpha runs over not traceless, over 4-dimensional quaternions with norm P, integral of course. So this sum over alpha has 8 times P plus 1 elements, number of ways of writing P is a sum of 4 squares. So it's a sum of length P. And this causes lots of issues because in reality, we're going to have absolute value squared of this sort of thing, but we want just absolute value squared of Fourier coefficients. And applying Cauchy is a terrible idea because now our Hecke relation doesn't have 2 terms, it has P terms. So this will cause trouble. But okay, let's try to implement the strategy and see where it leads. So
which case will we focus on? The case greater than or equal to K or the case less or equal to K?
Yeah, so let's say the case greater or equal to K because this obstruction is a bit clearer in this case.
But it's not that one of them is clearly easier than the other somehow.
In some cases, yes. So there are several cases for which Hecke operator we have to use, and yes, but you don't do anything. So the proof is by recursion. So you don't do anything unless you do both cases. So somehow it's maybe illusory that one of the cases is easier.
Let's just understand something. That sum of betas over the Fourier coefficients, that's a vector. That's over vectors in Euclidean.
Yeah, that's over traceless quaternions now.
And you are using the primes P to dilate.
Yes, only the
And so far you haven't told me whether I'm using lambda 1 or lambda 2.
Yeah, so we're using lambda 1 because we're assuming we're in this baby case where lambda 1 are large. Yeah. And let's say of size 1 as well. They could be larger, but it's easier. All right, so for this highly divisible sum, if you recall before, we have to deal with, well, we're going to be a multiple of many, many primes. Let's try this easy case where let's see if we can treat the sum where we're multiple of 1 prime. And if you work things out, what we need is just to compare favorably with the sum over Z. Just this. And the issue here is that, well, you can't apply Cauchy because these guys will have very high multiplicity. But there is actually a nice way of applying Cauchy here because you can actually detect the multiplicities early and weight them down beforehand. So I'll define the set I of B. I think of it as the increasing set. Sorry, I of beta, the increasing set for beta. It's the set of the relevant alphas that are going to show up here of norm P, such that the exponent of P in this conjugate is greater than the starting one. And this is bounded by hand or by unique factorization of quaternions. It turns out to be a size of most 16. We have 8 units, so it's really a size of most 2. Basically, because this forces beta to have an alpha bar in the left or an alpha in the right. Okay, that's very false, but that's roughly how you may think of this. There's non-commutative unique factorization for quaternions, so it's a bit messy, but things work out. All right, so why is this relevant at all for this? Well, it turns out that this set is the set that's really prone to multiplicities. So we're going to really weigh it down. When we do Cauchy, we put the weight 1 over P. It's a bounded set, so it doesn't matter. So when we do Cauchy, we get these guys in our bad set, a bounded number, and most of them, well, we take the loss. Great. So when dealing with this sum, well, again, all we have the Hecke relation here. So we isolate this term here in the Hecke relation, show everything to the other side, apply Cauchy, etc. This term is fine, this term is fine. These guys are the star of the show. So we get this sort of sum. And we apply this, so we get multiplicities. M1 here is counting the ways of writing delta as this sort of conjugate for alphas in the increasing set, and M2 for alphas in the non-increasing set. Here, there could be many ways of writing M1 as for alphas in the increasing set. Of course, given alpha and of course delta beta is determined, but the key here is that M2 is bounded. So if alpha is not in the increasing set for beta, there can't be many coincidences between these guys for different primes. For different alphas. So there's only a bounded number of ways for writing delta as such a quotient for a pair alpha beta, such that alpha is not increasing for beta. So this is just some arithmetic. It's not complicated.
I would imagine that if you acted on the tree,
Mm-hmm.
because that's what's naturally this sum of 4 squares and the quaternions, that this kind of analysis, you would see how to carry this out in complete generality. I mean, this is an accidental isomorphism you're using with 2x2 matrices.
Right, yeah.
That's why I asked you, Pitali. It's also in Platonov and Rapinchuk's book that will give you different realizations of arithmetic groups, and they explain how you get them over quaternions.
But in general, you get a Clifford
I
algebra.
think you want to probably, in general, really use spherical functions because that's the spectrum. And that would involve sort of analyzing where you're on these buildings. And that's, I'd imagine, the right way to generalize this, which I'm sure you're wanting to do.
Yeah, so I can say more about this, but yeah, so yeah, so this is how we deal with this sort of issue in the case of this highly divisible sum. So a weighted form of Cauchy suffices, it turns out, but something else comes up, and this is still honestly quite mysterious. We don't have a very good abstract way of understanding it, but there must be one because it just works too well. So here's an interesting case. So, okay, maybe the lambda ones are all tiny. We have no control over that. we may be forced to use the lambda choose. So let's assume we're in that case. And let's say they're of size L, which is bounded away from 1. Great for all the primes for simplicity. Here's the first Hecke relation I just copied for your reference. The second one is something like this, roughly, plus irrelevant terms. All right, so we try to amplify with lambda 2. So let's consider now the non-highly divisible sum. So observe that I'm in the other case because it's easier to see this this issue. In this case,
Wait, why is alpha, beta, alpha bar divisible by p squared, or is?
it's not always. Yeah, so if it's not divisible, this guy is 0.
Oh.
Yeah. In fact, it wasn't always. Oh, sorry. Even here, it's not always.
Oh.
Yeah. And this sort of thing is really what's going on here. But of course, beta could be a multiple of p. So, but yeah, this is morally what's going on there. All right, so we try to amplify this thing. All right, so here is the non-highly divisible sum. Mk is just less than k prime factors. We again put this amplifier in. Great, so each guy here is size L. We have y to the 1/8 of them. And then, well, what do we try to do? We apply the Hecke relation here. These terms turn out to be fine, at least using weighted version of Cauchy. But for these terms, bad things happen to multiplicity no matter what weights you put. So no matter what weights you put in Cauchy-Schwarz here, you're going to have issues. You're going to have elements delta that can be written as this sort of conjugate in many different ways for many different primes p. These deltas won't have much structure that we can detect. They won't be multiples of many of these primes. They will be large. Yeah, so this, we were stuck for quite a while. And then there's something interesting that happens here, which is, well, there's a sort of Hail Mary move, which is we can try to switch the Hecke operator. So one observation is that this sum here, these conjugates sort of appear here as well, but if instead of beta we had beta p. So if we consider lambda 1 a beta p, we have this nice sum here, and then we pick up some extra terms, right? We pick up a of beta, and we pick up a of p squared beta. Now this is horrible if the eigenvalue L is say 1, because, well, we were trying to amplify a beta and we ended up with a beta. So this is quite bad, but if L is large, we have a little gain. So if L is sufficiently large, this move actually turns out to work. Of course, I'm not telling you what to do with this term that looks problematic, but something like what sound does actually works to deal with these sums along multiple actual rational primes.
Is this step you need to write p around twice the 1/8?
Yeah, well, it's just convenient for various reasons. It's convenient for first of all, we need to localize these primes. Well, the size of the eigenvalue. It's also convenient for knowing the size of the sum that we get. So yeah, you don't have to, but it's very technically convenient. And okay, this last step explains why 1/8 actually. So what if the eigenvalue is of size 1? Well, you can switch Hecke operators in a different way. This term here also appears as this term for p squared beta. And well, plus some stuff that's not so friendly. So plus this term times p squared, which looks even worse. But then we can actually apply the previous the previous relation with the first Hecke operator for p cubed beta here. And then we don't get a beta. We get something that looks even worse, a p squared beta. But this is not tautological, at least as a move. So you don't try to amplify a beta and get a beta. You get something that maybe looks even worse. But these sorts of sums we know how to get a little bit of gain by an argument that I'm not telling you. And this turns out to be, so this is quite bad because you still have lambda 2 here. So if L is huge, you expect to gain, or you need to gain this factor of L, and you're losing it here. But if L is 1, turns out to be fine, which is the case that we actually had to deal with. Yeah, so this is the strategy for dealing with lambda 2. The case in which lambda 3 is large is more technical, but no significant new difficulties show up. So this sort of observation is applicable there as well, and solves the problem.
Was there a reason to vote for such a thing?
No, so this is completely mysterious to us. I mean, we have some very vague ideas, but we don't completely understand what's going on here. In fact, we have to throw away some terms to make this work. So for instance, this term had to be thrown away and dealt with other ways, but this packet really doesn't want to be split by Cauchy. You only do that if you absolutely have to, which eventually you do have to, at least as far as I'm aware. Yeah, but so we're sort of switching conjugation for big powers of p, and it looks much worse. But it turns out that in these rays we can deal with things much better, which is something I'm not telling you how we do this, but it's very believable. And in the end, we get some sort of recursive inequality. In this case, we can't really apply induction as in the case of sound, but this actually explains where the extra logs come from. So you get some sort of recursive inequality for this function g, which we want to show is bounded by some powers of log uniformly, and you get something of this sort. So you can, yeah, if you're bored, you can solve it yourself. But this explains where the extra powers of log come from. They're sort of undefined, but they're bounded. Yeah, so something like this holds. All right, I think I should stop here.
Questions?
Can you deal with rank 2 cusps? I took SP2, SP4.
Yeah, so for higher rank,
because then there's a very similar theory. There's the Fourier coefficients, Ziegler modular forms, for example, and the Hecke operators operate in rays. So it seems all amplification and this kind of thing, where you're only trying to gain small powers, can be played on rays through the Fourier coefficient, which is what I think you're doing here.
So we can do GL3 for, so we can prove a comparison inequality for GL3. So this is the part that you're talking about. But it turns out to not imply non-escape of mass. It implies some weak distribution. And the reason is basically because you can think of this argument as integrating against an incomplete Eisenstein series. And then really you're doing Rankin-Selberg, right? So this is how you're getting positivity. You're trying to reduce to a rectangular domain. But the incomplete Eisenstein series for SL3, at least the minimal one, which is the one you need, is not in L infinity. So you don't get a uniform bound. So really the incomplete Eisenstein series is not covering the fundamental domain uniformly. It has very high multiplicity in some parts of the domain and there's multiplicity 1 in other parts. So we don't know a good way of covering this cuspidal region in such a way that we also have positivity because, well, we want to apply inequalities. Yeah, there are some ideas in a different direction.
So you have not handled any case which has a higher rank cusp?
Yeah, so higher rank, we don't know how to make the strategy work.
From my perspective, higher rank cusp is bigger. It's somehow.
What?
From my perspective, higher rank cusp is bigger. I mean, in rank 1, the cusp has basically, if you wish, entropy 1/2 or something, and then the higher rank case, it has entropy 1 minus 1 over d or something. Somehow, from my perspective, higher rank would be harder. But I mean, you could.
No, but I think this is a soft argument. Somehow I'm beginning, my feeling is the escape of mass is a soft argument.
Yeah, very much.
It should be soft.
It's hard to use anything hard because you have to be.
Yeah. So the whole point is playing with Hecke operators, which are only spectral things, and
I suspect of some geometry of the building that is.
The other thing that
And here, I mean, we don't see we see here some calculation, but we don't see what's behind the calculation that makes it.
I'm sure there's some theorem about spherical functions that you can create that's the analog of lambda p squared, but in several variables, which is some identities one.
From my point of view,
that part is easy. Yeah, creating
I understand the building in higher end, and also here, the point is that it's not exactly about spherical functions of the building, which is higher end, because.
No, it's a relation between that and the cusp, obviously.
Exactly, so that there is.
So
I think the amplification methods are clear to us in terms of the geometry of the building. That's not the problem. So,
I have a very general and conventional question. So this Hecke eigenfunctions that just choice of eigenbasis for the general eigenspace. So suppose I perturb my operator by perturbing the metric. The eigenvalue is split. The basis is unique. The escape of mass probably still works. Non-escapable mass. But what about ergodicity?
Okay, so for SL2, I can talk about SL2R. I think there it's conjecture that the eigenspaces are dimension 1. So in fact, like passing to this arithmetic version of the conjecture should be the same as the general version of the conjecture. Of course, like proving that seems very difficult. I don't know exactly what the situation is for other groups.
I think what you're asking is take a locally symmetric space and perturb it in the middle, keeping the cusp constant, I would assume.
Yeah.
And then you're asking, does escape of mass, can you control it under perturbation?
Well, the escape of mass should control it. So
I agree.
But do the split up eigenfunctions close to Hecke eigenfunctions?
This is a very subtle question. I don't know. Mueller studied a lot about, and Ralph Phillips also, perturbing locally symmetric space hyperbolic in the compact part. And he showed that there is the proof of analytic continuation of Eisenstein series by Lax and Phillips was used by Mueller to show that you can analytically continue the Eisenstein series with variable curvature in it, because it's a compact perturbation. But those are much weaker theorems than this. So that has been developed. The Eisenstein series is what we're talking about, but this is a subtle question. It's interesting. So what happens with 5?
Yeah, so for 5, I think the Hecke theory could maybe be pieced together, but at least in these explicit.
Using the quaternionic, what are you using?
Right, so for 5, there's still an accidental isomorphism, which is nice, but the Hecke theory is an absolute nightmare. It's possible that the methods apply, but we haven't tried. So I think it would be good to understand this a bit more conceptually. It's also unclear if this accidental isomorphism is really vital. It might not be, but it's very technically convenient. So.
Yeah, just a small curiosity, but is there anything known in any special case if you don't have, if you're not in the arithmetic case about the general conjecture?
So I'm definitely the wrong person to answer that question. given the people who are in the room, but I think considerably weaker statements, but there's a lot of progress.
There are some
different
theorems
fields.
found using fractal uncertainty that are quite good about the support of any of these measures must have full topological support. That's using fractal, that's Dyatlov and others. And then Nalini and Antaraman has proved not that they equidistribute, but that so this would get away from arithmetic. But she hasn't proved that, she's proved that it's positive entropy. Yeah, those don't use arithmetic, and that's of course attractive for some people and unattractive for others.
What are some results when you have only one Hecke operator? So that's somehow somewhere in between. It's not clear to me whether one can expect this kind of non-escape of mass to work if you have only one Hecke operator.
Yeah, but
Any insight of that?
so I tried a little bit. Okay, we definitely don't need.
You're not going to amplify with one prime.
Exactly. Okay, I mean, the only idea I had is that if Ramanujan fails, then amplifying with one prime is much more powerful. And we know how to do things with hard methods if we have Ramanujan. But yeah, the two things don't seem to come together. So there's a gap. But I don't know. Yeah. So yeah. So the equidistribution results are available with just one prime.
More questions? So let's thanks the speaker again.